Hi everyone, welcome to One Stop Mathematical Solution. Today we are going to solve CSIR NET Mathematics June 2013 question paper. In this video, we have only dealt with the abstract algebra part. First question, question 21. Let G be a simple group of order 168. What is the number of subgroups of G of order 7? We have given a simple group and its order is given. We have to find how many subgroups are there of order 7. So first of all, we look into the concepts used in the question. So G being a simple group implies G neither have a proper normal subgroup nor a non-trivial subgroup. That is, G only have a trivial and improper subgroup. That is, it has only E and G as its normal subgroup. Third silo theorem states the number of p silo subgroup of a group G is found using this formula, NP is equal to 1 plus pk, where 1 plus pk should divide order of G divided by p. And if p silo subgroups are unique, if and only if p silo subgroup is normal subgroup. So let us solve the question now. So we have given order of G to be 168. So we have to find the number of 7 silo subgroups. So I am writing 168 in multiples of 7. So that is equal to 7 into 24. Now we are finding how many 7 silo subgroups are there. So we are using the third silo theorem. So using that, we'll get N7 is equal to 1 plus 7k, where 1 plus 7k should divide order of G by 7. So that is equal to 24. So 1 plus 7k should divide 24. This is only possible for k is equal to 0 or k is equal to 1. Suppose if k is equal to 0, then number of 7 silo subgroup will be 1. That is, we get a unique 7 silo subgroup. That implies 7 silo subgroup will be normal. But this will be a contradiction for G being a simple group. So therefore, k should be 1. Therefore, number of 7 silo subgroup is equal to 1 plus 7 into 1, that is equal to 8. So now we'll check the correct option now. So we got 8 subgroups of order 7. So our option is third one. Next question, question 38. Which of the following rings is principal ideal domain? So we have given 4 options. We have to find which of them is principal ideal domain. So first of all, we'll look into the concept that is used in the question. So field means it's a commutative ring with unity in which every non-zero element is unit. Unit means every non-zero element should have a multiplicative inverse in that ring. And if f is a field, then f of x is PID. PID means principal ideal domain. And if f is integral domain, that is commutative ring with unity and with no zero divisors, then f of x is PID if and only if f is field. And R is PID if it is an integral domain. Also, every ideal should be principal ideal. Principal ideal means the ideal should be generated by single element. So we look option wise now. So first option is whether q of xy by x is PID. So we know q of xy by x is isomorphic to q of y. We know Q is field, therefore by the second concept, Q of y is PID. So first option is PID. Now we'll look the second option, Z plus Z is PID. So we know if a field is PID, then it should be an integral domain. But this set fails to be an integral domain. I am taking 2 elements from that. So 1 0 and minus 1 0. When I am adding these both, I am getting this is equal to 0. So Z plus Z is a ring with 0 divisor. That means this ring is not an integral domain. Therefore, this cannot be a PID. Now we'll look into the next two options. Whether Z of X is PID. PID means every ideal should be generated by a single element. So if we look this 2 comma x ideal, this is obviously an ideal, and this is equal to set of all 2 into p of x plus x q of x, such that p of x q of x element of z of x. So I am telling that this is not generated by a single element. I am using a contradiction method to prove this. So suppose this ideal is generated by a single element f, then f should divide 2 and f should divide x. So this will implies f is equal to plus or minus 1. So this is contradiction to be in f being a single element. So 2 comma x is not a principal ideal. Therefore, z of x is not PID. Also, you can use this third concept, that is, we know z is an integral domain. Therefore, z of x is PID if and only if z is field. But z is not a field. Therefore, z of x is not a PID. So third option is also wrong. Last option, M2 of Z is PID, that is 2 by 2 matrix whose elements come from integers. So this is also failed to be an integral domain. So I am taking two non-zero elements from that. So that is equal to A is equal to 1 0 0 0 and B is equal to 0 0 0 1. Now I am multiplying both the matrices. When I multiply this, I am getting this is equal to 0. So this is having a 0 divisor. That means this is a ring with 0 divisor, which implies this is not an integral domain. So if it is not an integral domain, then it cannot be a PID. So now we'll check the correct option now. So the correct option we got is the first one. Next question, question 90. Let sigma is equal to 1, 2, 3, 4, 5 and tau is equal to 1, 2, 3, 4, 5, 6 be permutations in S6, the group of permutation on 6 symbols. Which of the following are true? So we have given two permutation from the symmetric group of S6 symbols. Then we have to find which of the following is satisfied by both of them. So first of all, we will look into the concept used in the question. So if A is an element of order n, then we can write A power n is equal to E, and also the cyclic group generated by A is equal to set of all E, A square, A cube, etc. up to A power n minus 1. Second concept, if order of A is equal to n, then A power n minus 1 is equal to A power minus 1. And if two cycles are conjugate, if they have same cyclic decomposition, that is, the cycle should be of same length. And two cycles, sigma and tau, commute if sigma tau is equal to tau sigma. That is like commutative property, it should be satisfied. Now we will move on to the question. So we have given sigma is equal to 1, 2, 3, 4, 5. So order of sigma is equal to LCM of the lengths of the cycles. That is, first one is like 2 cycle, second one is 3 cycle. So this is equal to LCM of 3, 2, that is equal to 6. So sigma power 6 is equal to E. So the cyclic group generated by sigma is equal to set of all E, sigma, sigma square, sigma cube, sigma 4, sigma power 5. If we write sigma square, that will be equal to E. So already I have written that E. Now we will find sigma square, sigma cube, sigma 4 and sigma power 5. Sigma square is multiply sigma into sigma. So I am writing sigmas. So 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. So we are multiplying these two permutations. So now when we look here, the second sigma, 1 is mapped to 2 and in first one 2 is mapped to 1, so 1 is mapped to 1 itself, and again now 2 is mapped to 1 and 1 is mapped to 2, so 2 is mapped to 2 itself. Now 3 is mapped to 4 and 4 is mapped to 5, so 3 is mapped to 5. Now check for 5. 5 is mapped to 3, 3 is mapped to 4, so 5 is mapped to 4. Now check for 4. 4 is mapped to 5, 5 is mapped to 3. So this cycle completes. So sigma square is equal to 354. Now we are finding sigma cube, that is equal to sigma square into sigma. So I am substituting sigma square and sigma, so that is equal to 354 into 1, 2, 3, 4, 5. So consider the sigma here. So 1 is mapped to 2 here. Here 2 is mapped to 2 itself. So 1 is mapped to 2. Here 2 is mapped to 1 and 1 is mapped to 1 here. So 1 is mapped to 2. So this is closed. Now 3 is mapped to 4. Here 4 is mapped to 3. So totally 3 is mapped to 3. Now 4 is mapped to 5. 5 is mapped to 4. So 4 is mapped to 4. Now 5 is mapped to 3. 3 is mapped to 5. So 5 is mapped to 5. So we'll get sigma cube is equal to 1, 2. To find sigma power 4, I am using this concept. Okay, sigma power 4 is equal to sigma minus 2. So that is what we'll get from that formula. So sigma minus power minus 2 means sigma square, inverse of sigma square. So we are finding the inverse of this permutation. To find the inverse of sigma square, now fix the element 3 and write interchange these two elements. So we'll get 3, 4, 5 as sigma power 4. Okay. Now sigma power 5, as before we are using that formula, so we'll get this is equal to sigma power minus 1. So sigma inverse of sigma. So we'll find the inverse of sigma. So sigma is given here. So to find the inverse, we'll fix, so 2 cycles inverse is same itself, so need not change the elements. And for the 3 cycle, we are fixing the first element 3, then interchange these two, so we'll get 3, 5, 4. So totally we'll get sigma power 5 is equal to 1, 2, 3, 5, 4. Therefore the cyclic group generated by sigma is equal to E 1, 2, 3, 4, 5, 3, 5, 4, 1, 2, 3, 4, 5, 1, 2, 3, 5, 4. Now we'll write the order description table for sigma. So here I have not included the identity. You know the identity's order is every time 2. So I have not included that. All other elements are included in the order description table. So I am looking for number of elements of order 2. So when we check here, there is only one element of order 2. Now order 3, number of elements of order 3. So order 3 number of element is 2, 3 cycles are there. So 2 number of element is 2. Now number of elements of order 6. So that is like, this is like split into 2 cycles. So the least common multiple of those cycles length. So 2 in 2, 3, that is equal to 6. For this also the cycle length is LCM of 2, 3, that is also 6. So we will get number of elements of order 6 is equal to 2. So this is the order description table for sigma. Similarly, we are finding the cyclic group generated by tau and its order description table. Here I have not detailedly told about the cyclic group generated by tau, but you guys have to check whether these elements are coming and find the order description table for tau. So order description table is, when we check, it is similar to the order description table for sigma, and also not the cardinality of sigma and tau is also same. So the subgroups generated by sigma and tau are isomorphic to each other. Now they have also asked the cyclic group generated by sigma intersection tau's value. So when we find its intersection, we are only getting the identity, which is the trivial group. Now sigma is equal to 1, 2, 3, 4, 5, 6. So its cyclic decomposition is given by first cycle's length is 2, second cycle length is 3, then 1. So the cyclic decomposition is 2, 3, 1. Similarly, for cycle decomposition of tau is like 6. These two are not equal. If they are equal, that cyclic decomposition of tau should be like 2, 3, 1. But here it is like 6. So they do not have same cyclic decomposition. Therefore, they are not conjugate to each other. Now we will look the last option. Now sigma is equal to 1, 2, 3, 4, 5 and tau is equal to 1, 2, 3, 4, 5, 6. Now we will find the value of sigma tau, that is equal to 1, 2, 3, 4, 5 into 1, 2, 3, 4, 5. So we are multiplying both these permutations. So check the second cycle, that is tau. So here 1 is mapped to 2. In sigma 2 is mapped to 1. So totally 1 is mapped to 1. Now check for 2 in tau. So 2 is mapped to 3. Here 3 is mapped to 4. So 2 is mapped to 4 totally. Now check for 4. 4 is mapped to 5. Here 5 is mapped to 3. So 4 is mapped to 3. Now check for 3. 3 is mapped to 4. Here 4 is mapped to 5. So 3 is mapped to 5. Now here 5 is mapped to 6. 6 is mapped to 6 itself. Because here it is not written. So it will be mapped to itself. So 5 is mapped to 6. Now check for 6. 6 is mapped to 1. 1 is mapped to 2 here. So the cycle is closed now. So similarly, find it for tau sigma. Have written the value here. So when we check, sigma tau and tau sigma's values are not equal. Therefore, sigma tau not equal to tau sigma. Therefore, sigma and tau do not commute, because for commuting, the commutative property should be satisfied. So now we will check the correct options now. So the correct option we got are 1 and 3. Next question, question 91. Let Sn denote the symmetric group on n symbols. The group S3 plus Z by 2Z is isomorphic to which of the following groups? So we have given a group and we have to find to which of the option it is isomorphic. So first of all, we will look into the concepts used in the question. So we know that Z by NZ is isomorphic to NZ. And G1 plus G2 is abelian if and only if both G1 and G2 are abelian. If either one of them fails to be abelian, then the external product is also fails to be abelian. And third, cardinality of G1 plus G2 is equal to cardinality of G1 cross cardinality of G2. Sn is non-abelian for n greater than or equal to 3. And note that S3 is the smallest non-abelian group. And we know that Zn is abelian because Zn is always cyclic. So cyclic implies abelian. For G1, G2 element of G1 plus G2, we have cardinality of G1, G2 is equal to LCM of cardinality of G1 in group G1 and cardinality of G2 in group G2. And Dn is non-abelian group of order 2n. Two groups are isomorphic if they have same cardinality and have same structure. Now we look into the question now. S3 plus Z by 2Z. Now we know Z by NZ is isomorphic to NZ. So Z by 2Z is isomorphic to Z2. So this is isomorphic to Z3 plus Z2. And we know S3 is smallest non-abelian group. So this implies S3 plus Z2 is non-abelian. We know that external direct product is abelian only if both are abelian from the concept 2. Now we are finding cardinality. Cardinality of S3 plus Z2 is equal to cardinality of Z3 into cardinality of Z2. We know cardinality of Sn is equal to n factorial. So cardinality of S3 is 3 factorial. Cardinality of Zn is n. So cardinality of Z2 is equal to 2. Therefore, this is equal to 3 factorial into 2. So, the value is 12. So, first option is Z by 12Z. We know Z by NZ is isomorphic to NZ. So, Z by 12Z is isomorphic to Z12. We know Zn is always abelian. So, Z12 is abelian. So, the given group cannot be isomorphic to this group because the given group is non-abelian and this group is abelian. So next option is like same as above. Z by 6Z plus Z by 2Z is isomorphic to Z6 plus Z2. Both Z6 and Z2 are abelian. Therefore, Z6 plus Z2 is abelian. So similar to the above concept, the given group is non-abelian, but this group is abelian. So both cannot be isomorphic. Now third option is about A4. Now A4 has only elements of order 1, that is the identity, and 2, the product of 2 cycles, and 3 of 3 cycles. Note that cycles of odd length is even permutation and cycles of even length is odd permutation. So I am just telling how I found out this. So now we have to write the partition of 4. So 4 can be partitioned into 5 ways. So that is equal to 1 plus 1 plus 1 plus 1. So this is representing the identity permutation. So this is like of odd length. So this is the even permutation. So order of the identity is found by the LCM of this partition's number. So 1, 1, 1, 1, that is equal to 1. So identity's order is 1. Now next one, 1 plus 2. This is 2 cycles. This is an odd permutation. We know A4 only contain even permutation. So I have only found the order of the even permutation here. Now this can be written also as 2 plus 2. This is like product of 2 cycles. We know when we add 2 odd permutation, we are getting an even permutation. So this is an even permutation. I'm finding its order. So taking its LCM of 2, 2, that is equal to 2. Now this is equal to again 1 plus 3. This is like 3 cycle. So using this is an even permutation. So order of 3 cycle is least common multiple of 1, 3. So that is equal to 3. So this is again can be written as 4. 4 is an even length cycle. So this is an odd permutation. So we not check the order for here because we are only concerned about even permutation. Like this, I found the orders of this elements in A4. So A4 only has elements of order 1, 2 and 3. Okay. So now we consider an element in S3 plus Z2 as 1, 2, 3, 1. Now I'm finding the order of this element. So cardinality of 1, 2, 3, 1 is equal to LCM of cardinality of 1, 2, 3 in S3 and cardinality of 1 in Z2. We know this is a 3 cycle. So this cardinality will be 3 in S3. So that is LCM of 3, comma. The cardinality of 1 in Z2 is 2 because when we add 1 2 times only, then we'll get the identity element. So this is equal to 2 cardinality. So this is equal to LCM of 3, 2. So we'll get this as 6. But in A4 we do not have an element of order 6. So this is like so the group A4 cannot be isomorphic to S3 plus Z2. So obviously the last option will be correct. That is S3 plus Z2 will be isomorphic to the group D6. And we know D6 is a non-abelian group of order 12 by this concept. Therefore, the correct option is the fourth one. Next question, question 93. Which of the polynomials are irreducible over the given rings? So we have given 4 options. We have to find which of them are irreducible over the given rings. So first of all, we'll look into the concept used in the question. So Einstein criteria, if f of x is a polynomial which is written as a0 plus a1x plus a2x square plus etc. up to an x power n, then if there exists a prime number p such that p divides ai for all 0 less than or equal to I less than or equal to n minus 1, but p does not divides an and p square does not divides a0, the constant term, then f of x is irreducible over q. And f is a field and f of x element of f of x is a polynomial of degree 2 or 3, then f of x is irreducible over f if and only if f doesn't have a 0 over f. So now we'll look into the options one by one. So first option is x power 5 plus 3x power 4 plus 9x plus 15 over q. So I am using Einstein criteria here. So when we use that, we'll find an prime 3 which divides 15, 9, 3, but it does not divides 1, and 3 square does not divides the constant term. Therefore, by Einstein criteria, it is irreducible over q. Now, the second polynomial is x cube plus 2x square plus x plus 1 over z7, integer modulo 7. So for this I am using the second concept, that is f of x is irreducible if and only if f doesn't have a 0 over f. That is, if we put numbers of z7 in place of x, we shouldn't get 0 as a value. So I am just putting the value 0, 1, 2, 3 etc. up to 6. So when we put like that, we are getting f of 3 is equal to 49, and 49 modulo 7 is 0. So 3 is a 0 of f of x in z7. Therefore f of x is not irreducible. That is, f of x is reducible over z7. So second option cannot happen. Now third option, x cube plus x square plus x plus 1. From first two terms I am taking x square common. So we'll get x square into x plus 1 plus x plus 1. Now x plus 1 is common for these two. So I am taking x plus 1 outside. So we'll get x plus 1 into x square plus 1. This is obviously reducible over z because we are getting a factor which is an element of z. Now the last option, x power 4 plus x cube plus x square plus x plus 1. This is obviously irreducible over z because we cannot pair terms. So now we'll check the correct options. So the correct options are 1 and 4.